Hello, everyone. Welcome back for our second day of the 2020 Latin American Space Challenge online conference. So today we will have the teams making their pitch deck presentation about the LASC challenges for 2020. It is important to say that the 2020 Latin American Space Challenge is being held online with a sprint-like event because of the COVID-19 pandemics. Let's do some history between the decision from LASC organization and the teams from making the 2020 Latin American Space Challenge an online event with a sprint-like uh, day. So in August, we talked with our team leaders. We had 4 meetings with them to talk about what we could do for maintaining the Latin American Space Challenge and making it safe. So we achieved some interesting milestones, creating a new format. It's an online format. So this online format is about with the teams picking a challenge and developing a solution for this challenge. So on November 2020, on November, we announced the challenge on YouTube. Each team had 24 hours for picking a challenge. And on November 23rd, we published the teams and the challenge that they picked. And today they will present the solutions for the challenge. So they had 7 days for developing the challenges and their solutions. Let's talk just about the challenge. We have 5 challenges for the 2020 Latin American Space Challenge sprint-like event. The first one is the satellite monitoring for the Northeast Brazil oil spill. So just a simple overview, the challenge is we had a oil spill in northeastern Brazil that is an ongoing spill of crude oil that has affected Brazilian jurisdictional waters and in northeastern Brazil. The oil leak was located in a specific coordinate, and the challenge for the teams was to develop a small satellite solution for being launched in maximum 6 weeks for the monitoring of the affected areas. The second challenge is a responsive launch capability of small sats for monitoring of rainforest wildfires, Amazon and Pantanal deforestation, monitoring Peruvian borders, and a lot of things that you can do with a satellite applications. And the task for the teams was to develop a small sat solution for a low Earth orbital with a payload capability up to 150 kilograms. The third one is about deforestation in the Amazon. So the challenge for the teams was to develop an infrastructure made of a small satellite constellation equipped with a optical and infrared cameras, allowing them for a real-time surveillance of the Amazon biome. The fourth challenge is about the moon race and the Latin America. So the main challenge is to develop a brand new disruptive space mission concept for going to the moon by 2024 with the Artemis III. So this was our fourth challenge. The fifth challenge, in my opinion, is the most challenge one, is about the reusable rockets, revolution, or I can't say this wording, guys, I'm sleeping. So it's about reusable rockets, but we did not have any chance picking these challenges, so I'm not going to talk a lot about it. So these were our challenges for this year. Welcome, everyone. Thank you for your time. Now I will pass the word to Gabriel Yamato, and he will talk about our schedule for today.
Hello, everyone. Good morning. For today's agenda, we have some presentations from the team. Starting now at 8:15, we have our first team presentation, team ID 9. Then we have team ID 6, 32, 3, and 1. We will have a break at 9:30 to 9:45, and we will be back 9:45 to 11 for the second part, for the second round of the team presentations. For the second part, we have team ID 13, 36, 15, 12, 11. We will have a break at 11 and get back only at 2 p.m. for the third part. So please be aware and check the conference schedule and check when your team will be presenting the challenges results. And for the part 3 is from 2 p.m. to 3:15. We have team ID 16, 19, 17, 26. For the part 4, we are going to start to 3:30 to 4:30, and for the part 5 from 5:15 to 6 p.m. So if you have any question when your team will be presenting, please be in contact with the LASC organization team, and also please see the online conference schedule. And finally, the most exciting part of the event, at 8 p.m. to 9 p.m. tonight, we have the final part with the award ceremony. So we will have the LASC team closing the 2020 Latin American Space Challenge online conference with the Conduct Award, the Sportsmanship Award, and the Spirit Award. We also have the Technical Awards, the Category Awards, and finally the big prize, the 2020 LASC Online overall winner. So again, if you have any questions, please be in contact with the LASC organization team. And also we are on live on YouTube. You can use the live chat to be in contact directly with us as well. Thank you very much. Good luck for all teams, and let's go.
Hello, everyone. We are back to our 2020 Latin American Space Challenge conference. Today, we will have the teams making their presentation about the solution for a specific challenge. Now we will have the team 6, Bizu. They will present about a solution for the challenge about the responsive launch capability of small sats. So they will have 10 minutes to present their pitch deck. And good luck for Team 6. Bizu, now the word is with you. Good luck.
Thank you, Calvin. Good morning, everyone. My name is Arthur, and I'm going to present you the Bizu pitch deck for the LASC challenge number 2, the responsive launch capabilities of small sats. So what we need here is to develop a low Earth orbit small sats launch vehicle with flexible and rapid management to prevent ecological catastrophes. We must support a payload of 150 kilograms and launch it from the Alcantara Launch Center before August 2021. The content of our presentation starts with the vehicle proposal, then the concept of operations, the logistics, and investments with a business model. We have two focuses for this project. First is the requirement of the mission that was set by our stakeholders. Then we focus on precision, because most of the artificial satellites occupies these orbits, and soon there will be much more of them. And due to this, precision is needed for avoidance of collision and additional debris generation. With this, we look for two main solutions for our challenge. The first is like a must, because there is a partnership between private and public institutions, because there's no other way to launch before August 2021. This will ensure cheap, flexible, and rapid launch services by using technology already developed or still in development in Brazil. Then, look for an optimal solution. We will use a reusable system, providing essential reduction in cost per launch. However, it will require a higher development cost. This means that we will recover some systems that we will show here. So as we are building a very cool rocket and we needed a very cool name, and as the competition happens at the Latin America, we named the rocket as the Latin American bird of prey Harpia, because it's one of the largest and most powerful of the world. So this is an overview of the Harpia launcher. It's important to note that all propulsion systems are already developed or still in development in Brazil. The first and second stages use a S50 solid motor. The third stage uses a S44 solid motor that was used on the VLS project. The VLS is the first Brazilian launcher vehicle. And the upper stage is the first Brazilian liquid rocket engine, the L5, propulsed by LOX and ethanol with a pressure-fed system. We must highlight on this picture these blue sections between after the first stage and after the second stage, because they contain the recovery and separation systems. The first and second stages will be recovered with parachutes and then refurbished for financial economy and post-flight examination of the engines. Also, for the stage separation technology, we will use a clamp band that was developed for the VLS-1. We now will follow for our guidance and navigation systems that starts with a thrust vector actuator system on the first and second stages, also derived from VLS-1. The TVA does not control rolling. Still, the rocket can be controlled due to the use of a very fast hydraulic actuators on the first and second stages. The third stage is controlled by a cold gas, and for roll deceleration after the third stage, a yo-yo system is activated. This yo-yo system was also developed here for the VSB-30. The guidance of the upper stage is performed by gimbaling the L5 engine. For the logistics of the operation, we first start with the Alcantara Launch Center bases. This is the operational base in Alcantara. This is a tracking base in Raposa, and this is an administrative one in São Luís. On the operational base, we have 4 main areas: the airstrip, where the motors will arrive; the military villages, where the team will stay during the whole operation; the telemetry tracking and command facilities; and finally, the launch and preparation sectors. The motor arrives at the CLA airstrip and follows this path until the SPL. The same follows for the payload and the fairing, and all of them will be integrated, prepared, and launched at the SPL. This is the platform that will be used for the launch. The main parts here are the ML, that's the launch table, where the rocket is integrated on the vertical, the umbilical tower, and the integration mobile tower that protects the launcher from environmental hazards. Our concept of operations has 2 phases: the integration and the pre-launch, launch and flight. Harpia is integrated partially on the horizontal and on the vertical positions. All pre-launch, launch and tracking activities will be performed at the CLA facilities. Firstly, the pre-integration tests of the solid motors occur at the launch and preparation sector. The payload is integrated to the fairing by the client, and its final integration to the upper stage happens on the payload preparation facility at CLA. Then, the solid stages are assembled at the thruster preparation facility, and a special trailer is used to carry them and hoist them to assemble on the integration mobile tower. The motors are then moved from the trailer to the launch table by a crane at the tower. This cycle is repeated for the other S50 and the S44. After that, the last integration phase connects the upper stage to the launcher body, using the same crane. The main pre-launch activity is the loading of the upper stage tanks that's performed with 2 trucks, for ethanol and for LOX, and 2 pumps. The control and command activity is performed at a blockhouse near the platform. So these are flight CONOPS. The first motor burns for about 82 seconds, and the first stage is then separated. The first S50 opens the parachute for recovery, and the second stage is burned for another 82 seconds. The second S50 also opens a parachute after separation, and the fairing separates right after the second stage ends the burning. The empty S44 burns while falling through the atmosphere. Then, the L5 engine takes our payload to the chosen orbit. And here on the right, you can see the estimated speeds after each propulsion system ends the burn. Finally, the recovery of the S50 will be performed with the support of both the Navy and the Air Force of Brazil. Now, to get to our business model, we estimated the initial costs for development, the fixed costs to keep the company running, and the variable costs per launch. With this, we could determine a price per launch that would make us break even with more than 2 launches per year. This graph showed the evolution of the income and expenses per year in a linear model of growth in launches. We highlight here the break-even point of the company and the maximum exposition of about $6 million. So this is our team, and we thank you all for the opportunity of presenting our project here. And now we want to check if you have, and these are references that we use to get all the public information that we use on the presentation. And now we want to know if we have any questions.
Nice solution. We were talking here about your proposition is complete. You talked about the technical part of the engineering of developing a launch vehicle. You talked about the CONOPS, the concept of the operations. You talked about the financial part. So your team made a complete solution when we talk about a pitch deck. It's very interesting. Let's imagine that we are like investors, and your break-even is around the third to the fourth year, maybe the 3.5 years after the start of the company, correct? Your break-even.
Yeah, at the year 3.
The year 3. So between the year 0 and the year 3, you have the death valley of a startup. So with that in mind, and knowing the ecosystems of startups, and mainly the space startups in Brazil, what you have in mind for searching a partner? For example, we know that the government is already developing the S50 and the VLM. So what are you thinking about to get the investment from where, specifically for this Death Valley, for example?
For the Death Valley, as you said, I think that in the beginning of all space programs, the government invest is the main importance. And as we are seeing nowadays, a lot of satellite projects that are AAB and the Brazilian Space Agency is investing. I think that they are our first investors in this case, because they are paying for a lot of satellites, but they don't have how to launch those satellites. So we are proposing them a solution for the satellites. And as you can see here, our price per kilogram is almost the same as Rocket Labs. That their price is about $23,000 per kilogram. So I think that our first investor here would be the the Brazilian Space Agency, just because they need to launch their satellites.
Nice. Congratulations. Sincerely, I loved your presentation, the solution that you bring to us. So congratulations, and that's it. Thank you, Arthur. Thank you, Roberto, Ronaldo, Juliana, Octavio, Rafael, Davi. Nice project. Congratulations.
Thank you.
Thanks, all.
Hello, everyone. We are back with our 2020 Latin American Space Challenge Conference. Now we will have the pitch deck presentation of Team ID number 1, Minerva from UFRJ. They will present their solution for the responsive launch capability of small sats challenge. So we have with us Larissa Mush. So Larissa, when you are ready, please go on. Good luck.
Thank you. Hey everyone, I'm Larissa from Urasu Rockets, and I will present our idea for responsive launch capability of small sats. First, present your company. Our name comes from Tupi-Guarani and means RP, a Latin American eagle that figures between the largest and most powerful raptors in the world. And our team began in Rockets, University Rocket team, and we understood the necessity to connect the academic world and the aerospace industry to join force to hit the aerospace program in Brazil. This is our team, everybody from Minerva Rockets to UFRJ. This is our roadmap of our idea with problem, solution, market studies, financial, and execution. For motivation, we noticed that monitoring biomass, deforestation, and borders were current problems in South America. Many times needing a quick decision-making to make an action. And satellites can be the key to achieve this objective. And considering this is our timeline where science recognize the problem, look up for solution, implementation, conclusion. And considering that recent disasters as oil spill in northwestern of Brazil warned our country to the necessity of a quick action to acquire data from these events and to take a strategic action with satellites could have a good application. In this scenario, to optimize our data acquisition from satellite service would be interest to launch a flexible vehicle until August 2021 from Alcântara Launch Center with up to 150 kilograms of payload capability. And our idea for solution this problem is airdrop launch of a Brazilian rocket with some adaptations from a cargo bay of a C-17 during the flight. Some considerations about market studies. This is not a new idea. This was already tested for Falcon SLV for Falcon program, where Falcon SLV mockup was dropped from cargo bay of C-17 and was the heaviest single object ever dropped. For consider air launch, we need to look for another types of launch. Analyzing that, the ground launch is very common in the industry, but depends a lot of the weather conditions, air adaptations, and have high structured costs. For water launch, is not so utilized. Depends on the climatic conditions and sea conditions, and have complicated logistics to deploy a new launch system, and have high costs too. So air launch shows up as a no operation and method for no companies. Don't depend the weather, which is suitable for rapid launch, and because don't need as much engine power as the ground to get out of inertia. So we choose air launch. For passing for the vehicle, for the which carrier aircraft, we think about, we compare KC390, C17, and C5, considering their cost, maximum payload, and service sailing. The C390 haven't the cargo dimensions needed to rockets inside. So we choose C17 as the most qualified aircraft to this operation. So as a rocket passing for the vehicle choice, we consider Brazilian projects think about high mass and technology developed. And pick VS50 with adaptation plus a third stage of L5, a liquid motor. So why we choose this combination? Second, some delta analysis. This combination could reach 300 kilometers in LEO, and both are tested, made, and developed in Brazil. It could improve the Brazilian aerospace program and technology, and reduce the design and test times because both are made in Brazil. Even if this rocket needs electronic adaptation for ignition and control trajectory systems. So, as a SWOT analysis, air launch allows more flexibility, speed, and depends less on climatic conditions and adaptations of the base area. And operation was tested, engine was tested too, and as weakness, we necessary to validate the combination of L5 and VS50, and have short time to project design and execution. As opportunity, we have less environmental impacts around the base. The base industry could be developed, and Brazilian technical force too, and could put us on a map for an option for aerospace launches. As streets, we have possible low investment, resistance of the industry to share reports for us, and a serious accident could end the whole project. This is our timeline project. Think about security. It's necessary to have some tests like mock-up drop test and a rocket dropper test with guidance and inner propellant to guarantee the security before the launch day. As competitors in the market, we have Stratolaunch and Launcher One. Both are air launches vehicles. As launch centers, we have Cape Canaveral, Gideon Center Launch, and Cheyenne Space Center, and that this launch could occur. Talking about financials and budgets, we have a business model based on cost structure, like satellites launch missions, maintain the technical team, and movement the base industry around Brazil. As key metric is to monitor our project and quality. We have deadline, resource, and value added. And as a unique proposition, unique value proposition, we have a 150 kilograms payload to reach around 300 kilometers on LEO. It's a rocket flexible and with a speed launch from CLA until August 2021, having operation and manufacturing with Brazilian technology. For the custom segments, we have Brazilian aerospace industry, ministry in Brazil, and for foreign, we have aerospace industry and governments too. So we think about costs and estimates this operation in 3 parts, with launch vehicle, launch operation, and flight operations. Total cost around $17 million, and an investment based on $23 million. And for execution and this operation, we made a model, size the pre-launch to the post-launch, size the load of the cargo bay, drop box, aircraft nose, drugs deployment, rocket exits, fuel fall, first stage ignition, launch altitude, and post-launch. 3 times of launch operation, and based on this picture, you could understand the operation, size, the takeoff of the airplane, until the satellite separation. Oh, thanks. Does anyone have any questions?
Okay, so we have a nice presentation from Larissa from team ID number 1, Minerva Rockets, Minerva Welfare J. So congratulations on your presentation. I just have a question from our LASC team. The question is about let me ask you, if the solution of the launching from an airplane, the airdrop, it's so good, because why this is not so used on the market today? So what are the negative points of this solution, in your opinion, and in the opinion of your team?
So it's not common in industry, because another country have basic good infrastructure basis. We don't have to us to use the ground base, the ground launch. We need to have some adaptations on our base in technology questions, and the negative aspects of our idea, it needs to validate both motor and PS50 as a rocket, and we don't know if it could be due in the time until the August 2021.
Thank you so much, Larissa. Our team, we don't have any other questions. I just want to congratulate you. It was a beautiful presentation, wonderful, with a lot of motivation. Congratulations, and good luck, and congratulations for your pitch deck. Nice.
Okay, thank you. Nice.
Hey,
Hello everyone. We are back for the 2020 Latin American Space Challenge Conference. Here we are having our teams presenting their solutions for the few challenges that we suggested for them. So now we will have the team ID number 13, Cosmos Foguete Modelismo, and they will talk about satellite monitoring for the Northeast Brazil oil spill. So this will be a 10 minutes presentation of the pitch deck, and we will have Vinicius starting their talk. So Vinicius, good morning. The time is yours. You can start. So you have 10 minutes. Good luck.
Thanks. Hello, everyone. My name is Vinicius. I'm the captain of Cosmos Foguete Modelismo, the Rocket 13 based in Universidade Federal de Santa Catarina from Joinville, Brazil. Today, we're going to talk a bit about the satellite monitoring of the northeastern Brazilian oil spill. To show you a bit about the presentation, first, we're going to talk about the oil spill itself, the disaster, then how we're going to analyze this disaster with our satellites. Then we are going to show how we are going to construct and project the satellites. And lastly, we are going to show you how we're going to the logistics and the planning involved in the launching of the satellites in a very short amount of time. Talking a bit about the disaster itself, you can see that it is based on the coast of Ceará, around 200 kilometers from the coast. The origin of this disaster has not yet been confirmed, but all leads point to a cargo ship leaking the oil in the ocean. An estimated amount of 40,000 tons of oil have already leaked into the ocean, contaminating an area of around 8,500 square kilometers. Comparing this spill to other major spills that happen in the world and in Brazil, you can see that comparing this to the biggest oil spill that happened in the coast of Europe, the Prestige oil spill that happened in 2002, you can see that our spill is around 60% amount of oil of that one. Comparing it to the spill that happened in 2010 in the Deepwater Horizon platform in the Gulf of Mexico, you can see that our oil spill is a lot smaller than that. It's 20 times smaller, but that's not to minimize the problem. It's still a very big disaster. We will destroy the coast of the northeastern region of Brazil. Comparing this to the last year's oil spill, you can see that we have 8 times more oil this year, and another aggravation, other problem that we have, it is a lot closer to the coast. Last year's spill was 730 kilometers from the coast, while this year's spill is 200 kilometers from the coast. Here we can see the potential spill trajectory that will follow in the next weeks. Considering the historical maritime currents in the region and historical wind trajectory in the region as well, we can see that the spill will move towards the states of Tocantins and Maranhão, contaminating the coast all the way from Fortaleza to São Luís.
Okay, now talking about the spill analysis. For the spill analysis, we use 2 main methods, SAR and COMS. Synthetic aperture radar, also known as SAR, is the main satellite sensor, and its function is to generate images of the oil spill. It's a radar system that uses emission of microwaves to generate imaging of the target. There are some advantages using the SAR system. One of them is that this technology works regardless of daylight or weather condition. This means that SAR can generate images even at night or through clouds and rain. Here's how SAR works. An articulated mechanical arm will open and unfold the mesh reflector antenna at the end. Pulses of radio waves are emitted by antenna to the mesh reflector, which aims then to the target, and the reflection of each pulse is received by the same antenna. And with that, it's possible to calculate the geometry of the target. As well as SAR, the spectrometer emits and receives electromagnetic waves. But this device doesn't create an image. Instead, it analyzes some properties of the oil, such as hydrocarbon composition, the thermal condition, and the layer thickness. The advantage of using such a system is that it gives a much greater depth to the spill analysis. Besides, the thermal study can cover some of the false positives generated by SAR.
Okay, so now we are going to talk about the technical parts of our satellites. We use a pair of antennas in each satellite. The first one is used to transmit and receive the data of orbit control, altitude control, yaw, and propulsion orders. The transmission, in other words, the communication, starts on the Satellite Control Center in São Paulo, which is responsible for all the parameters calculations. After that, goes to the Alcântara ground station and finally to both satellites. The second one is used just to transmit the data of both sensors in each satellite to the Alcântara ground station, and finally goes directly to the Federal Emergency Management Agency in Brasília. We've developed a pair of 12 EU satellites. The main structure is made of aluminum alloy. We use 2 pairs of compressed gas thrusters in each satellite for maneuver purposes, and an onboard computer system for control in each satellite as well. The mission is scheduled to be 2 years long, and after that, the propulsion system will be activated to move the satellites towards the atmosphere to burn.
Okay, so for thermal control, we chose a multi-layer insulation method using aluminized polyamide foil, commercially known as Captain, to cover the exterior panels and thus protecting the spacecraft from the outside harsh environment. Captain has actually been widely used in the aerospace industry since the Apollo era for this exact purpose. Inside the spacecraft, as you can see, heat-sensitive components are fixed with a thermal strap made out of high-conductivity graphite fiber in order to conduct and dissipate heat to the outside. Our satellite is powered by this nano-powered BPX battery, which is commercially available and flight-proven for reliability. It is capable of delivering up to 29.6 volts and storing 77 watts-hour of power, enough to power all sensors during its short period of intense activity in each orbit and maintain all vital systems functioning for the entirety of the mission. Since lithium-ion batteries are very sensitive to temperature, it has its own heater in order to maintain a constant operating temperature. Our batteries are recharged by 2 triple arrays of solar panels laterally deployed once the spacecraft reaches orbit. This method allows us to maximize the area of the solar panels while still maintaining the compact size of the spacecraft for launch. And here we can see a model of the satellite and its main components as indicated. This model was made by our team during the week, and it's a pretty accurate representation of what will be the final product and its different configurations for launch and after full deployment.
So, moving on to the launching phase. Firstly, it's important to notice that our satellites will describe a non-geosynchronous and equatorial orbit, being able to capture the oil spill each time it completes a turn around Earth. In addition, since the sensors required a 500 kilometer of altitude, this was the chosen orbit altitude as well, classified as a low Earth orbit. Given the calculated speed at this height, we concluded that the satellites will be able to collect the data every 1 hour and 39 minutes. Finally, since the standard angulation wouldn't be able to cover the whole oil spill area, we calculated 2 different roll angles for each satellite, being one with 13 degrees and another with 26 degrees. And when used as described, not only will it be possible to have a complete coverage of the oil spill and its trajectory, but also it will give us a safety margin that will avoid gaps in the analysis. As far as the launch is concerned, we chose Virgin Orbit as our payload launching company. They have this new breakthrough launching program that will fit all of our needs, since they work with low Earth orbit for small payloads up to 500 kilograms. And their solution is to launch the rocket that will carry our CubeSat through a Boeing 747-400 after it reaches an altitude of 10 kilometers. This will give us a lot of flexibility, since this will allow us to have any inclination that we want for the orbit, and also a lot of financial savings as well, due to the fact that this type of launch reduces drastically the fuel consumption. In order for this to happen, we first need to send the package to Long Beach, California, where the headquarters of Virgin Orbit is located. Then they will send it to their base in Guam, which is an island in the Pacific near the equator line. And from there, they will depart to the Boeing and start the launch. Since prices for rocket launches are humongous, we decided to ask for financial support to NGOs such as WWF and Water Organization. They are used to give this kind of resorts for this kind of missions. Just Water Organization have already given about $13 million for those kind of projects. To conclude, here's just a table comparing the price of one big satellite and our solution with 2 smaller satellites. So as you can see, there's a huge difference in price, but it's still something that we need the support from those kind of organizations or governmental resources. And here is just a schedule to illustrate how our chronogram will work during the weeks from manufacturing until launch. Thank you.
I would like to thank everyone here listening and here to the presentation for your presence. We from Cosmos are very happy to take part in the 2020 LASC Online.
thank you very much, Vinicius and the entire Cosmos team. It was an excellent presentation. We really like the way you presented. You introduced the problem, talked about the technical solutions, the financial execution, and we have a few questions. First one is about the orbital parameters. I would like to know if you guys did some calculation or even idea of what is the decay time. So how long it takes to satellite decay after the orbit insertion for these parameters that you said. It's like 1 year, 2 years, 5 years.
Yes, we have program for that. For that, to answer that question, I'm going to call my buddy JP. That was the one taking part in this problem during the week. João Pedro.
Yes, and I will call my teammate Leonardo to answer that.
Okay. Hello, everyone. So yeah, we estimate 2 years duration of the satellite, its lifetime. And also we did all the calculations based on the altitude that the sensor would capture. So we knew that the sensor will capture an altitude of 500 kilometers. So we did all the calculations based on this altitude.
Perfect. So 2 years. Great.
Yeah, yes. The satellite itself has a propulsion system that will then push the satellite towards the atmosphere, then to burn and re-entry.
Great. I saw that you guys also design a quick CAD model of the project. I would like to know what was the big challenge for this project. What do you think will be the big challenge to make this project real?
To make this project real, the real challenge would be the short amount of time that we have to launch the satellite. Just the time we have to launch the satellite that was given by the LASC organization was 6 weeks. This is a very hard time to make it happen in real life. There are not really many companies that would be able to make available this sort of launch and satellite and rocket launch available in this short amount of time. Would need a lot of government pressure in these things and these companies to be able to make that happen.
Yes, perfect. So thank you very much, Vinicius, Rafael, Leonardo, Lucas, and everyone, the entire Cosmos teams. It was a really good presentation, really like it, and thank you very much for the presentation.
Thanks, Gabriel. It's a pleasure to be a part of this competition. It was really fun, and it's a lot of hard work, but it's really nice to be a part of this competition and the LASC Online. Thanks.
Hello, everyone. We are back with our next presentation. It will be Team 36 from Minerva. They will talk about deforestation in the Amazon. So before introducing the team, I just want to make a kind of reminder that the presentations are excellent. We had already 3 teams, and they did a great job. So I'm very proud of everyone. So we will have João Duarte from Minerva, team 36, talking about their pitch deck. So João, good morning. You can start your presentation. You have 10 minutes. The time is yours. So good luck.
Hello, Calvin. I would like to thank you and all the Latin American Space Challenge organization team for this opportunity of being here. And I'm going to talk about our mission, YAISAT, named after the Brazilian native Yai constellation. That's Tucano's language for jaguar, the Brazilian native animal. And I'm here representing the Minerva SATS team from Federal University of Rio de Janeiro. And I'm going to present, first of all, our status report, then the mission approach, some financial aspects, a comparison with other products, our business model, and some risks management that we calculated. Well, our problem is deforestation in the Amazon rainforest. In the image on the left, we can check that deforestation had increased even more since 98 in comparison with deforestation up to 97. And in the graph on the right, we can check that in the past 2 years, the deforestation has increased exponentially compared to the previous years. This triggers some issues related to national economics. There is an example here where Europe threatens trade retaliation due to deforestation in Brazil. The chart on the right shows the dependence of the economy on exports to Europe, and the one on the left shows the importance of exporting agricultural products, with 42% of the exportations to Europe being agri-food. So for this problem, we propose using a Walker constellation composed of 20 3U CubeSats distributed evenly on 5 orbital planes with some synchronous orbits, inclined in 97 degrees, taking images with space resolution of 31 meters. This constellation will have an average revisit time of 10 hours and will be able to completely cover the Amazon in 1 day. And today we have the Leaders mission with 2 satellites with 64 meters of space resolution and no infrared sensors. So the surveillance gets blocked by the clouds. And it is a partnership of one Brazilian satellite and one Indian satellite. So our mission will add to this project images with resolution of 31 meters. We will use infrared sensors, so we will be able to monitor through clouded skies. And we'll have a smaller revisit time due to being a constellation of CubeSats, and will be a product 100% Brazilian. So our business model will be based on the operation of our system and collecting images. Then we would sell those images and data to our potential clients, such as military, institutes, landowners, big corporations, government, and non-profit organizations. And they will pay monthly to use the database generated by our system, and that will be our income. So a quick mission overview here. We will have 2 sensors, Gecko operating on the visible spectrum with field of view of approximately 9.15 degrees and a swath of 64 kilometers. And the FLIR-TAU sensor operating on the short wave infrared spectrum of the light with swath of 294 kilometers. The orbits will have 92.6 minutes of period. The satellites will be launched with 46.3 minutes of interval, and each of them doing 15.5 revolutions per day. We will also have 3 ground stations, one in Ecuador, Cotopaxi, the other 2 in Brazil, one in Belém, and the other one in Cuiabá. With those parameters, we used the Savoir software, and we simulated those orbits being this rectangle on the surface, our area of interest, that's Amazon, And those circles, blue, red, and yellow, are the ranges of each of our ground stations. We made a study about our budget, and with the satellite fabrication, we would spend slightly less than $2.2 million. With 5 years of operation, will be spent $1.5 million with ground stations, 4.5 million with engineering and personnel, 5.9 million with launches, giving this a total amount of approximately 2.8 million per year. And for our risk management, we used the NVPR model. It is a qualitative model with score for determined parameters, giving a security score for determined areas of analysis, such as user, technical, and market. On our analysis, we had a high score for user risk, despite a low score for market, giving us a 66% chance of successful business. As we would be a new company in the business, we would be classified as a new venture company. For the market study, we used the NanoSats database and selected the ones that uses CubeSat services, such as big corporations, university for research, and military forces. From the market survey, we selected these segments due to their objective, and big corporations and landowners would use our services to testify their environmental friendship and avoid economic sanctions, such the one we commented earlier with Europe. We checked for successful missions with specifications like ours, and Aerospace Corp launched the Cumulus payload in the ISARA mission with the same sensors and was able to do urban and fire monitoring. Also, Planet Labs used 28 FreeU CubeSats to do a continuous stream of imagery, being able to identify areas for disaster relief and monitor deforestation as well. We also estimated the income for a price per user and per square kilometers of $2.2. That is 8.3% cheaper than market average. So estimating 100 users during the whole 5 years plan, we can have a slightly more than $2.3 million of gross profit. And that is it. This is our team. I'd like to thank all of them for the great work. I'm João Duarte, the Chief Information Officer. And on behalf of them, we would like to thank you for this amazing opportunity to introduce YAISAT, and we hope we can make a difference in the current framework and stop the degradation of our planet. So if you guys have any questions.
Nice presentation, João Duarte. We loved your motivation and engagement, showing the ISAT idea for the monitoring of deforestation in the Amazon. It's nice. Just doing some overview here, and you say if we are correctly. You said a constellation of about 20 satellites, correct?
Yeah.
Okay. Okay, perfect. I don't have any questions. I think you approach everything that we asked for the challenge and for the pitch deck. Let me see if any of my colleagues, if they have any questions. So,
perfect.
Any questions? Okay. I think you did a great work. We do not have any question. So congratulations for your presentation, João. Congratulations for your team, for the dedication and engagement for making this part of the work being real, your presentation, and also for the dedication in this time of pandemics. Congratulations and good luck.
Thank you so much.
we're back with the 2020 Latin America Space Challenge Conference. For this pitch deck, we're hosting Apex Rocketry Team 12. They're going to talk about the moon racing in Latin America. Are you ready, Caio?
Yeah, sure, Vitor. Can I start?
Yeah, so you have 10 minutes, and at the end we'll have a few questions. The word is yours.
Okay, thanks, Vitor, and thanks everyone. My name is Caio, and I'll be talking to you about Apex's proposal of an experiment to extract vital gases from the lunar soil. Sorry, just a moment here. For 48 years, no man or woman has stepped on the moon. Since then, many questions have been asked about our capability of advancing into space. Do we have enough scientific knowledge about the lunar environment? Is our current technology capable of maintaining permanent lunar infrastructure? Or maybe more importantly, should scientists, engineers, and entrepreneurs even be thinking about new space ventures when there is a global warming crisis here on Earth? Well, both space infrastructure and the renewables industry have a very important common link, which are efficient, low-cost thermal control solutions. Our proposed experimental payload for the Artemis Iii mission seeks to link all of these topics together by using a passive, meaning with no moving parts, so a passive heat transfer system to extract volatile gases from the lunar regolith, the lunar soil. Okay, so Apollo data indicates that vital gases like nitrogen, hydrogen, and water vapor could be trapped inside the lunar soil. It is also thought that helium could be extracted from lunar regolith, potentially being a future source of nuclear fuel. Dr. Harrison Schmidt identified two methods of extracting volatile gases: heating the regolith and mechanically agitating its granular structure. The main idea behind Apex's payload is establishing a controlled flow of regolith through a countercurrent heat exchanger. As the cold regolith, the cold lunar soil falls down through the device, it heats the internal piping, while at the same time being heated by such pipes, releasing gases through heat and agitation. An array of electronic heaters is placed in the middle of the device, heating the regolith to its maximum temperature and releasing most of the trapped gases, resulting in a hot waste regolith. Apollo technology simply discarded this hot waste. It, however, still has large amounts of thermal energy, which can be recuperated and given back to the upstream cold regolith, increasing the overall efficiency of the entire heat exchanger. This is precisely what our experiment does. Pulsating heat pipes are a novel technology capable of transferring heat without the use of pumps or compressors. They're simply an array of copper alloy pipes filled with potassium fluid. Pockets of potassium liquid and vapor are formed inside the heat pipe, and when it receives heat from the waste regolith, these fluid bubbles begin to oscillate, transferring heat through advection and diffusion from the heat pipe's hot end to its cold end. Well, besides the piping and the heaters, Apex's payloads includes a CPU and communications unit with a touchscreen interface, load cells and electronic valves to control the regolith flow, and thermocouples to capture temperature data, as well as an electronic space-grade compressor and canister to store the volatile gases extracted from the soil. The whole structure weighs roughly 5 kilos and can handle up to 50 kilos of regolith, which is 2 times the expected amount of material used in nominal operations, all the while being compact and foldable. We've sought to use composite and metal materials familiar to rocket design teams in this project. Especially relevant are the experiment's paneling made of carbon and ceramic, which are both lightweight and a thermal insulator. Through a reduced order lump capacitance model, we've estimated that our experiment can recover 65 to 85% of the total wasted thermal energy, being much more efficient than the Apollo tests, consuming only 30 kilowatts of electricity instead of 350 kilowatts needed without the pulsating heat pipes. All of this while operating entirely on the moon in real time, while the Apollo tests were conducted on massive furnaces here on Earth. Well, okay, but where does Latin America come into this picture? Well, in 2006, Brazil sent its first astronaut to the International Space Station. 2 of the experiments he carried out in space were designed by UFSC, our university, and dealt with passive thermal control mechanisms. In fact, a mini heat pipe was tested. Our pulsating heat pipe idea follows in its footsteps, counting on 15 years of advances and studies based on the data obtained during the Centenario mission. which we have partially used to develop our proposed experiment here. Okay. The 2024 Artemis III mission intends to fly the first woman plus another crewmate to the moon's south pole. Its main objective is sampling lunar ice and exploring new techniques for future Mars missions. The mission will have a dedicated module orbiting the moon, onto which the astronaut's capsule will dock before descending to the moon. Some mining equipment and other equipment, such as rovers, will already be stationed on lunar soil before the astronauts arrive. And the astronauts will only carry 100 kilograms of scientific equipment. The astronauts will have a very limited amount of time on the surface of the moon, only 16 hours in 5 days. On the ground, the astronauts will have to assemble the foldable structure outside the lunar module, connect the experiment to the module's power bank with a capacity of 81 kilowatts, and initiate preheating and startup procedures. Apollo astronauts took about 2 hours to mine 20 kilograms of regolith. We estimate that with modern spacesuits, this time can be cut in half. Our experimental heat exchanger can process 5 kilograms of regolith per second, consuming 20 kilos in 4 seconds. Considering the mining and setup time, the whole experiment will take up about 1.5 hours. If the experiment is successful, it will be able to process almost as much regolith as has been tested on the Earth in the last 50 years, all the while operating entirely on the moon. Plus, if the experiment will take the information of 20 kilos of regolith and transform it into 3 grams of volatile gases, a reduction of 1,000 times in mass, which will make the return flight home much more efficient. Okay. In order to tackle the broad problems of gaining more scientific knowledge about the lunar soil, while also developing sustainable technology for terrestrial and lunar enterprises, we're proposing here 3 different technology phases, through which we intend to turn an academic idea into a meaningful business venture. To kickstart the project, we have the scientific phase, whose main objective is developing the previously described passive thermal control system, ultimately producing scientific articles, theses, as well as technology patents. For financing, we could seek Brazilian institutions such as CAPES and the Brazilian Space Agency. Apex's technical team members, as well as other UFSC students, could work alongside the university's established research labs, which have already sent thermal control experiments to the International Space Station. I myself had the opportunity of working on one such project that flew on the Centenary mission, and I can tell you that advancing this type of research really is very exciting. Overall, we estimate that our lunar experiment manufacture would cost roughly $7,000, with the set of electrical heaters being the highest expense. We expect that 3 to 4 prototypes of the experiment could be manufactured before launch. Taking into account the institutional costs of a 3-year-long research and development program, we can place the overall project cost at about $180,000, almost $1 million reais, which is a very reasonable figure for big scientific projects within the Brazilian federal universities, especially if business ventures are also involved. After the completion of the Artemis III mission, our project could evolve into the startup phase. During this phase, we could apply the lessons learned from the Artemis mission to develop energy-efficient thermal control systems for terrestrial applications. Photovoltaic panels for solar farms, or even for telecommunication satellites, could be an area of focus for the startup team. This type of application also has relatively high thermal gradients, and the vital electronics that control such panels must operate below a maximum temperature threshold. Heat pipe systems can be a profitable option to effectively cool solar panels. For initial support, we could turn to Brazilian institutions such as Sebrae-Tech, ACAT, and SC2C Aero, the latter of which is an academic and business joint venture based in UFSC, designed to kickstart up-and-coming aerospace technologies. Well, now, within a decade, the startup could consolidate itself into a profitable company, providing cost-effective thermal management solutions for the renewable energy and new space industries. The company could work on green aircraft, for example, developing cooling solutions for energy-dense batteries needed to power electric flights. Another application can be the passive cooling of rocket engine nozzles, which could result in lighter nozzle structures and lower liftoff weights. In the long run, solutions such as the heat pipe system we've proposed and discussed here could be used in solar farms on the Earth and Moon, on cislunar satellite constellations, and even on lunar habitats, all of which have a hot and a cold side and high thermal gradients that must be controlled. If the mining experiment really proves to be useful, then the extraction of volatile gases could sustain human life in lunar habitats. Moreover, lunar helium could serve as a nuclear fuel for future fusion reactors on Earth. That is, of course, if nuclear technology also evolves rapidly in the near future. All of these factors, combined with constantly advancing thermal research in space, could thrust Latin America into the new space race, all the while using space technology to improve conditions here on Earth and to help combat the global climate crisis. Ooh. Well, everyone, that's it. Thank you. If you have any questions, I'm here for that.
Okay, Caio. Thank you for your presentation. So you have a really innovative solution. It serves humanity with good data. You base yourself in a solution with facts. You talked about business, profitability. I think it was a really good presentation. For the last team, we don't have any specific questions. I'd like to thank you for your presentation. I can say that we're going to have a really tough time scoring all the pitch decks. The presentations are already good. And thanks again, Caio. Really good work.
Okay, thank you. Bye.
time! We are back, guys. We are back. 2020 Latin American Space Challenge back with the Team 11 Mission INGA. They are from the State University of Campinas, the UNICAP from São Paulo, Brazil. We are glad to have here Rafael Cota. He will be presenting the challenge, the solution of the challenge that the Team 11 Antares has picked for our challenge part of the event. They will propose a solution for the responsive launch capability of small sats. So good morning, Rafael. How are you doing today?
Good morning. I'm fine. And you, Calvin? How are you?
Nice. Thank you so much for asking, Rafael. So you have 10 minutes for this presentation, for this pitch deck. We hope good luck for you. So when you are ready, please go on.
Okay, perfect. So thanks. So first, I want to thank you for this opportunity to be here. Actually, it's a pleasure to be here presenting with the Team Antares, because this is the first time the Team Antares is participating in the LASC competition, and we are learning a lot from this competition through all the progress of the competition, not just from the organization, but from the other teams. It's really impressive, the work of the other teams. I'm really impressed, and we're learning a lot. And thanks again. So let's start with the solution of the problem. So we choose the challenge of the responsible capabilities for the small sat. And to start, first we need to understand the problems. What are the problems that we need to mitigate, to solve? And when we see the problems here, we can see through all the Latin American some problems, including the damage of the environment. So forest fires and oil spill oil in the sea, and deforestation of the rainforest and other forests. And this is the problem. The main problem here, actually, is to mitigate or to monitor these damages. And when you're here in the LASC, in Latin American Space Challenge, in this aerospace environment, we can see that are many teams that have the potential to produce some satellites, some small sats to monitor these problems. And actually here, as you can see in early presentations, this is really a potential for other teams. But when they have the potential to produce these small sats, these products to monitor this. Sometimes the team don't have the potential and don't have the time to produce the way, or better, the vehicle to make these satellites, these small sats, reach the low orbit, the orbit to monitor these environments. So, with that in mind, the team Antares have a solution to propose here. And we call the solution, or better, the rocket here, the launcher, LSV. If you have the eye of tiger, you can see this is almost an anagram for the VLS, Brazilian launcher of the small sats. This is a way to honor this rocket, because it's a really good project, and we hope that more and more we can see more technology from Brazil we're improving in the aerospace area. So, about the solution. First, this solution, the SV, needs to have the capability to carry 150 kilogram payload for the small sat. This is a requirement of the participation of the mission. Also, the team proposed that this rocket will be a solid rocket, because it's the knowledge that it's more proximity of the knowledge of the team, and we can work with more comfort ideas and with more environment, more comfortable environment with this rocket. Actually, in specific, the rocket will be a ammonium percolate solid rocket, because with mind as a solid rocket, the mass will be really big. So we need to find a solid propellant that's really effective to make this mission. So we propose the ammonium percolate rocket. Also, with that in mind, that is a solid rocket, we need to understand that it will be a four-stage rocket because of this mass. So the rocket don't need to carry all the mass through all the mission. So we propose this four-stage rocket because with this idea of the rocket with the solid propellant is a really good. And about more the operation of the flight, the first stage of the rocket, we reach approximately 40 kilometers height. The second stage is reach approximately 100 kilometer height. And the third stage will reach approximately to 300 kilometers height. And the last stage, it's reach the low orbit that we'll talk in the next slide. So about the mission, we need to take these small sats and take there to this low orbit. The low orbit is more like under the 2,000 kilometers height, but in specific, the team choose one type of low orbit that's really good, and we think this is a good idea. Is the sun-synchronous orbit. It's a orbit that is between the 600 and 800 kilometers altitude, and it's a good orbit because it's passed through the poles. It's almost a pole orbit, but the importance of this orbit that through the time of the day, the small sats pass through the surface at the same time of the day from each day. So it's good. It's a good orbit because this can show the progress of this deforestation of the oil spill during this same time of the day of which day. So it's a good idea to use this type to reach this orbit. So about the solution is this, and now about the concepts of operation. Here we had an idea of sort of how we'll be doing this work. So we gathered the idea and we start to gather the requirements with the stakeholders, with the companies that we will serve. After this, we will validate with the stakeholders and with the companies, and we start the preliminary project. So about the conceptual design, so on. And after this, we can validate again, and we can go to the detailed project. And this time, the work going to be really complex, and this time we need to be by the side of the stakeholders, by the side of the companies, to make sure that the rocket will reach any requirements that we'll need. After this, we can go to prototype manufacturing. So after this, the prototype manufacturing, we can validate this and go through the tests of the flight of the rocket and so on. And after the validation of the tests, we can present the final product. Is the LASC one, and to present the service and so on. And we can present the operation concepts of the flight, as I presented earlier. So the idea of the operation concepts for the progress of the project is here. And now we have the solution, now we have the operation concepts, but we need to have the logistics. But we need to have in mind the logistics. We need the transport, we need the material acquisitions, information exchange, the tests, and the launch day. Actually, some of the logistics that we need to have in mind. Also, because this is a project that will reach the Latin American, sometimes these types of logistics will need to need an exchange through some countries. So it's important to make sure that the logistics will happen. And the launching day, so the logistics of the launching day, it's the preparation, the validation test again, and ready to go. We can go fly with the rocket. We can make the product, and the small sats reach the low orbit. With that in mind, now we need to talk about the investments and the costs, because it's important too. And talking about the investments and the costs, we can see that this is really important to progress of the project. And in the first part, we need to talk about the structural elements. This is very important because it's not just the materials, but also the construction of the, for example, the body type, for the structure of the rocket, the nose, and so on, so on, so on. We need to talk about also of the electronic elements, because this we need a really, really, really potent telemetry and also a really good electronic system, avionics system for the flight. We need to talk about also the chemical supplies, because it's a monopercolate. It's important to note that it's really, really important to take care of this part of the chemical supplies. Also, the infrastructure and the tools, because of the size of this project and this test, sorry, the test too, but because of the size of this project and the size of this rocket, we need to take a special care of the tools that we use and the infrastructure. And also for the investment in research, because this type of project is really important. So we estimated a cost around $8 million. It's really a lot, but being other projects, being other proposals, as also the VLS, we can see this is not a lot bigger, and we have in mind this is the cost for the first project, the first ASV rocket, and it's a really good estimation, but also this is not the final estimation. And for the last presentation part is the business model. For the business model, we have in mind that after the solution, the operation concepts, the logistics, also the investments, we have in mind that this is a good solution because we can focus on produce a really good rocket, a rocket that is effective, a rocket that is good. We can present the service for the companies that we need to validate their small sats. So with in mind with this, and also with this type here that we have in this competition of correlation with other teams, with other companies, this is a really good environment to produce, to grow this type of market of the aerospatial market. And this is a really good time to present advantages as help expand this market, as also is a really good time to focus on the rocket. It's because this team is focused on the rocket, we can present a really good rocket, a really good solution. This is a solution, a business model that we need to take care. We need to stay closer to these stakeholders, to these companies that we do the service for, because we need to have in mind that we are just a way today to put the small sats in orbit, in low orbit, to monitor all this damaging environment that's really important to take care of. So this is a presentation. Thanks for our attention. Again, we are really excited to be here. It's a pleasure to present here. And actually, thank you again. We are growing. This is the first time we are here in the competition. We hope that each year we can grow, we can be better. This is, I thank you again for just not just for the company, not just for the organization, but for the all teams that are here presenting the solutions.
Thank you so much, Rafael Cota. Your presentation was very interesting. The entire team is the first time that the team is participating in the Latin American Space Challenge, and also for our side is we are very glad to have you and your team with us. So talking about your presentation, I have a question. You said that the project you estimated in about $8 million, correct?
Yeah.
For example, if your rocket project is approved by FINEP, for example, FINEP is a Brazilian government-based organization that supports a variety of projects. For example, if they talk to you saying, okay, you have the money for developing and build this rocket. So in your perspective, what are the main contractors in Brazil? When I say contractors, I'm saying the customers, okay, for contracting you for launching their payloads, for example.
Actually, this is a really good question. For the first thing, this will be a really good thing to happen, because also when the investments come for the project is a really good time. But the main contractors here in Brazil have grown this market of aerospace market, and we have some startups starting to study, starting to develop small sites and CubeSats and other types of sites. But here I have in mind some of them, but for example, the VSAT. And for this idea in mind that this type of market is growing here in Brazil, we have a really good opportunity to start growing within them. So it's just this in mind, but if the main contractors, we have, for example, the VSAT and any others, but this is an opportunity just not for them that are already in the market, but also for the other teams that are working, and other companies that are working to present their product as in the future, if maybe the PION too. It's for just example, just a joke. But to present this, we can, it's an opportunity to start growing with them and to make our product better with time, not just for them, not just them to make this, but also us to make this with them. I don't know if I answered the other part of the question, but what I have in mind is this.
Nice. Thank you so much, Rafael Cota, for your presentation. The answer, yes, you answered what I was talking about in this question. So congratulations. For those that is watching our live stream, Rafael Cota is also working not only in the Antares team for this Latin American Space Challenge and the other competitions, but also he is a PMO of the 2021 Latin American Space Challenge Cooperation. So Rafael Cota is also a PMO of our 5-kilometer target apogee rocket. So in 2021, we are together going to break get the student record for the South America of launching a rocket over 3 kilometers of apogee. So Rafael Cota, thank you so much for your presence, for the quality of your presentation, and good luck. Thank you so much. Now we are going to go for our lunch break, and we will be back at 14 o'clock Brazilian regional time. Thank you so much, guys. See you.